The valence shell electron pair repulsion theory, or VESPER, gives us an idea about the shapes of our molecules, but it doesn't explain why there are 4 equivalent bonds around carbon in methane. We have this tetrahedral shape, but carbon came in with an s and a p orbital, so how did it make 4 equivalent orbitals when the s and the p orbitals are on different energies? Well, to explain that, we need valence bond theory. Now, in a nutshell, valence bond theory tells us that a covalent bond is made by the overlap of half-filled atomic orbitals. So our hydrogen has one electron, and our carbon on this side will only have 1 electron, and that is a half-filled orbital, and it's overlapping, and that overlap is what creates the bond. Now, it should be fairly intuitive that this overlap will only occur when a portion of each orbital is going to occupy the same space. That should be the definition of overlap. But it also has to have the electrons that make an electron pair. There is a mutual attraction between the nuclei of each atom and the electrons themselves. And there is a sweet spot with a distance between the nuclei that creates a bond. Now, I won't require you to know any bond lengths beyond trends of bond lengths. Single bonds tend to be longer. This is a single bond, or a sigma bond, tends to be longer than a double bond, which contains a pi bond and a sigma bond, which is a little bit longer than a triple bond, which is a sigma bond with 2 pi's. So the more bonds there are between 2 atoms, the shorter those bonds will get. There is energy associated with both the making and the breaking of bonds. And typically, the breaking of bonds requires energy, and the making of bonds gives energy off. Now, s orbitals are spherical. And so when they overlap, we have this great overlap distance here. And that's what creates the sigma bond. A p orbital overlap is a little more creative. So when you have a p orbital, remember a p orbital is a dumbbell-shaped orbital, and we have this node where there is no chance of finding an electron. And when you have a p orbital overlap, it can overlap with an s orbital here, but when you have 2 p orbitals that overlap, an end-to-end overlap is not a good overlap. Overlapping like this, it's not a good overlap. So when we have p orbitals that bond, they will bond side by side. Well, that was very sloppy, but they will bond side by side so that there is a touching at both of the lobes of the orbital. This is what makes a pi bond. When 2 p orbitals overlap, we get a pi bond. Now, when you have something like HCl, and we've drawn this out before, we have 1 sigma bond, but we have no pi bonds. If we have something like oxygen, and oxygen is a diatomic element, that means in its elemental state there are 2 atoms joined together. This is 1 sigma bond and 1 pi bond. When we have something like nitrogen, nitrogen is another diatomic element. It exists as 2 atoms of nitrogen joined together. We have 1 sigma bond, but then we have 2 pi bonds. But let's go back to our methane example briefly. Now, methane is a carbon atom, and it has 4 equivalent hydrogen bonds. And I'm just going to draw it out flat in this case. They appear to be identical sigma bonds, but carbon's valence shell has an S2P2. Now we know this is 2s2P2, but we're just going to leave it as S2P2 for this moment. We have an empty p orbital. So if our px has 1 electron and py has 1 electron, then pz has none. So what happens is we promote an s electron up. And when we do that, we actually combine all of these orbitals. So here in this energy, if this is S and these are my p orbitals, we're going to combine these orbitals into 4 hybridized orbitals. They all have the same energy. Because they all have the same energy, then they are equivalent. And when we do that, we call that hybridized orbital an sp3 orbital. Now, sp3 orbitals, by definition, are only going to have sigma bonds. So these are sigma bonds. If we take our carbon example and we change this into, let's make this acetone. So acetone looks like this. There are 3 carbons in a line. The carbon in the middle, oops, not this one. The carbon in the middle is a carbonyl carbon. That means it is double bonded to oxygen, and I'm going to leave its lone pairs off and just kind of draw it like this. Now carbon still comes in with an S and its 3 p orbitals. But this time, one of those p orbitals is occupied. And in previous videos, I was coloring pi bonds, this pink-red color. So I'm going to do that again. So since this bond is a pi bond, we know that a pi bond is created when you have p orbital overlap. Since one of those p's is now occupied with the pi bond, now we don't have 3 p orbitals to hybridize. We only have 2. So these orbitals will hybridize, and now we have an sp2 hybridized carbon that makes sigma bonds. So these are sp2 sigma bonds. These orbitals are making the sigma bonds. The pi bond is made with a p orbital. Now the methyl groups here on the end of acetone, we consider those chemically equivalent. So I'm only going to look at the one. This carbon has 4 bonds. They are all 4 single bonds, which tells me I must have sp3 hybridized orbitals in order to make those 4 equivalent single bonds. So the bond here between the middle carbon and the end carbon is made by the overlap of a carbon sp2 orbital and a carbon, this one's sp2, and a carbon sp3 orbital. Carbon isn't the only atom that can hybridize. For example, what we have here, we have a pi bond and a sigma bond that are between these oxygen atoms. So oxygen comes in with the same oxygen comes in S2P4, but oxygen can form a pi bond, and that will use, it still has the S and 3 P's, and if it uses one of those P's as a pi bond, then the rest of the orbitals around it are going to be sp2 hybridized. So the sigma bond is an sp2 orbital, and the lone pairs are also in sp2 orbitals. The nitrogens here also come in with its S and 3 P's. This time we've used 2 of the P's to be pi bonds. So they're going to be overrun as pi bonds. So all we have left, and I put a P there, all we have left is an S and a P. Because that's all we have left, then the sigma bond as well as the lone pair exist in a nitrogen sp hybridized orbital. So if we go back to carbon, now carbon wants to make 4 bonds total. If all 4 of those bonds are sigma bonds and there are no pi bonds, then we are sp3 hybridized. We will have the same number of hybridized orbitals as we came in with. We came in with 1 s and 3 p orbitals. So we must have 4 sp3 orbitals to bond. If we have 3 sigma and 1 pi bond, then we are sp2 hybridized. That means we have used one of our p orbitals for a pi bond, so all that's left is what is hybridized, and we have an S and 2 P's, sp2. If we have 2 sigmas and 2 pi bonds, then we are sp hybridized. So we have used 2 p orbitals to create those pi bonds with their p orbital overlap side by side, and then what's left will hybridize. So all we're left with is S and P. So that is how the hybridization of carbon works. We will not have 1 sigma and 3 pi's. It's not going to happen. There's a similar hybrid pattern for oxygen. Of course, we're talking about another element completely, so there are some differences. But with oxygen, see, we have the lone pairs. So we're going to have 2 lone pairs, 2 sigma bonds. That's going to be sp3 hybridized. If we have 2 lone pairs and 1 sigma bond and 1 pi bond, well, then we're going to be sp2 hybridized.